This next session, we're going to talk about how do we prioritize endpoints for development and validation. And this is really the central question for this morning's work. So we'll have 5 speakers. They'll be speaking for 8 minutes each with 4 minutes for questions. So I will remind the speakers that we truly appreciate, and we truly appreciate the last session speakers for all staying on time. We will be strict about time limits. So our first speaker is Ted Maddess from the Institute for Neuroscience, the John Curtin School of Medical Research at Australia National University. And Ted will be talking here about challenges in measuring visual function, standardized effect sizes in pre-diabetic retinopathy patients, reproducibility and capacity to track changes, and interoperability of structural and functional changes.
Well, good morning. These are my financial disclosures. So I'm going to talk today about what I think are 5 key criteria for useful measures. These actually apply to structural tests just as much as functional. They're simplistic things, but I think they're not often talked about enough. The first one, and maybe the most important, is standardized effect sizes. We're looking for sizes around about 2 or better, which corresponds to area under ROC curves about 0.9 or better. And this is specifically looking at discrimination of controls from persons living with diabetes, but who have no DR yet. If we can't do that, then we've got no hope later. Multiple measures should be as uncorrelated with each other as possible, but correlated with the disease. We'll come back to that. High reproducibility to maximize the ability to track change over time. Good correlation of single measures with independent factors that occur within our complication screening variables, and ability to easily compare structure and function measures. This is something that's evolved over time. Okay, I'm going to spend the most time on this, standardized effect sizes. What we see here, we're going to look at, these are the names of the standard effect sizes, small to huge. We're going to look at the case of a medium effect size. This is often quantified by what's called Cohen's d, which gives you the relative separation of your patient and normal distributions. What I've got here is p-values for a given n. Of course, this is kind of meaningless in the clinic because n is always 1. You've only got 1 patient. But we concentrate on these numbers a little bit too much, I think. Then down here, we've got Hedges G, which is Cohen's d corrected for sample size. So I've used the same samples, 10, 20, and 30 patients. So what do you get from this degree of separation? Well, in terms of an ROC curve, at a sensitivity of 90%, you're misdiagnosing 3/4 of the normal population. That is going to destroy the healthcare system. Let's say we move to the large effect size. Things are a little bit better. Area under the curve still not so very good. Very large. You're still only at 80% area under the curve. 2. This is not too bad, but you notice here that these p-values are getting ridiculously small. We get excited about p-values over 0.05. We shouldn't be. So we really need to be at this sort of level or better. If we can get to an effect size of 3 or 4, that's what we need, but 2 at a minimum. So what I've done here, I've collected some data from a bunch of functional and structural tests. These are basically all comparing controls with people with no DR. Here's their Hedges G. Here's the equivalent area under the curve. And what you see is that none of them gets to the level that the most basic need. We need to see colors around here in the yellow. So this is a problem. Okay, this question of uncorrelated measures, this is actually kind of a simple idea. Of course, all the measures need to be correlated with diabetic damage. And this is because, of course, any disease is multifactorial. And these things should not be correlated with each other because they would be tests that characterize different aspects or different phases of the disease. They're measuring different things. So this can be related mathematically to what's called a likelihood ratio. You pick a sensitivity of interest and a false positive rate, you take their ratio. And typical for a test where you say have a sensitivity of 95% and a false positive rate of 5%. You get a likelihood ratio around 18, 19, 20, something like that. If you've got 2 tests that are perfectly uncorrelated with each other, but are correlated with the disease, your surety of diagnosis goes from 1 part in 18 to 1 part in 400. This is a very important concept. Of course, most measures are somewhat correlated, but that's just showing you in the limit. Good reproducibility. I mean, I've worked with glaucoma for a long time, and standard automated perimetry has notoriously high test-retest variability. That limits our capacity to track change over time. So the accepted dogma is that we have only an 80% chance of detecting rapidly progression patients if we test them 6 times in 2 years. Of course, no one does that clinically. And we do need to use perimetry or something equivalent in diabetes, but we need to be careful. Correlation with independent factors within the complication screening variables. This is something we've noticed, that if you take your standard bank of things like BMI, peripheral neuropathy, HbA1c, turns out that they contain about 3 independent factors, and different tests might be correlated with these different factors, and we can use this to our advantage. Match structure and function. Well, you've got 2 worlds. You've got perimetry world or things like it, and you've got structure, and these things have evolved completely independently, so it's bloody difficult to compare them. So why not, fix that? So I've just said all of this. So I'm going to tell you about one attempted fix. This is the quid pro quo. This is a device we're developing at the moment. What you see here is the stimuli being presented to the 2 eyes on 2 monitors. That'll be a little clearer shortly. So you see the 2 monitors there. We use mirrors to project them to the 2 eyes. And what we do is we video the pupils, which sounds like a completely crazy idea, but I can assure you that we've taken care of what most people are worried about in this. And you can see we're tracking the pupils in real time. This gives us an objective non-contact measure of function, which results in this, which is a bunch of impulse responses which you're not interested in. Basically, the amplitude of those things give you the sensitivity, and the time to peak gives you something you don't normally get in perimetry, the delay of the response, which turns out to be most important in retinal diseases. So what we've done is we've made a new stimulus. Everybody's probably familiar with the ETDRS grid. It's on every OCT. So why not make stimuli that just match that, right? So what we did, we just cut the ETDRS regions in half. We did that. Then you can easily compare structure and function, and you can compare the thickness and volume data with the sensitivities and delays I just told you about. And this test does both eyes concurrently in 82 seconds. And now we're doing things like OCTA in exactly the same regions so that we can compare them. Okay, so the conclusions, these are 5 simple criteria that we need to think about. OFA is an example of a test that meets all 5 criteria. And I've set out the criteria today. Let's knock my test off with something that's better. We've got a number of publications in diabetes. There's one being prepared on the 82-second test. This is one that we've just published on the 82-second test using the ETDRS stimulus in AMD. Works brilliantly. It's also done it in multiple sclerosis. Thanks for listening.